One is from Legae Academy, and it's called the Legae Academy Astronomy Club, and the other is from the Mauro Polo Space and Astronomy Club. These two clubs have submitted questions to our panel of experts, which is chaired by Prof. Mike Bode. The panel selected 6 of these questions to be answered this afternoon. The panel consists of Prof. Bode, who is the Deputy Chair of the ASB, of Dr. Muratlani Tsipa from UB, Dr. Rodri Evans of BIOST, Dr. Stuart Morongwe of BIOST, and Professor Fulvio Franchi of BIOST and from Italy. As you can see, a very erudite panel indeed. What's going to happen now is that a student will ask a question and will be answered by one of the panel members. After that, we'll allow a short discussion on the topic. We will invite the audience to join in if there's time. The time limit for the session is 60 minutes, which may mean we don't get through all the questions, but I'm going to try and keep pushing it so that we do. All right, so our first question is from the Legae Academy Astronomy Club, and it will be asked by Raza Hassan. He is an A2 student and he's president of the school club. Okay, Raza, over to you. Ask your question.
Good afternoon, everyone. My question, can you hear me?
Yes.
Okay. My question is, out of all the proposed theories about the end of the universe, which ones do astronomers believe to be most likely?
Thank you, Raza. And I'll ask Dr. Rodri Evans to answer that for you. Dr.
Okay.
Evans.
Thank you. So let me get my screen sharing sorted out. So hopefully you can see my first slide, and at the moment I'm just showing the question again. Out of all the proposed theories about the end of the universe, which ones do astronomers believe to be most likely? Can you all see my screen and hear me speaking?
Yeah.
I can, yeah.
Yes.
Okay, so just to give a little bit of history before we go to what we currently think. In 1927, a Belgian priest by the name of Georges Lemaitre, who's often now referred to as the father of the Big Bang, theoretically predicted that the universe is expanding. And this was experimentally confirmed by Edwin Hubble in 1929. He wasn't aware of Georges Lemaitre's work. In fact, most people weren't until the early 30s. This picture on the right shows Edwin Hubble in the middle, smoking his trademark pipe, Einstein at the eyepiece of the 100-inch Mount Wilson telescope, which was the telescope that Hubble used to make this discovery, and Humason, who was his observing assistant on the right. So the discovery that Hubble and Humason made, for a long time just attributed to Hubble himself, is that more distant galaxies appear to be moving away more quickly. So this is the original diagram that Hubble published in 1929, and I believe it was the proceedings of the Mount Wilson Observatory. So the most natural, simplest interpretation of this is that the universe is expanding if more distant objects are moving away more quickly. And the assumption for really most of the time since then was that gravity would slow down this expansion with a possible recollapse. So there is a link in general relativity, which Stuart knows a lot more about than me, which links the geometry of the universe to the to gravity and to the mass in the universe. So the 3 possible geometries are shown in this figure, so-called flat geometry. The middle diagram would be what we call an open geometry, and the top one a closed geometry. So the 3 possible futures for the universe are either a continued expansion but slowing down as it expands. So it would expand forever, but just take longer to do it, which, to use one of my favorite quotes from... no, I'll leave that. I can't remember the quote. So anyway, we refer to that would be the flat universe geometry. Another possibility is that the expansion stops and there's an ultimate recollapse. This would be a closed universe. And the third possibility is the expansion will continue, but more quickly than with a flat universe, and this is an open universe. So when I was a student, 30 odd years ago now, These were the three possible futures to the universe. Closed universe represented by the purple curve, a flat universe, the green curve. So don't be fooled that just because it's not a straight line, it is for a flat universe. It expands but slows down as it does so. And then finally, the red curve is the open universe, continued expansion, but more quickly than with the flat universe. I've remembered my quote now, so it's a Woody Allen quote, eternity is an awful long time, especially towards the end. So I always like to quote that. It's taking time to happen. Then by the 1980s, observational evidence and to a certain extent theoretical modeling suggested that the universe had a flat geometry. So people thought that we were right on this dividing line between the universe expanding forever and the universe ultimately stopping its expansion and re-collapsing. But this was all turned on its head in the late 1990s when there was a very surprising discovery, and that is that the universe's expansion appears to be accelerating. Now, this is still a controversial finding. People are trying to find other explanations, but basically, oh, sorry, I wouldn't. So what two separate teams found in the late 90s, based on several years of observations, was that very, very distant galaxies, which they were able to measure the distance of using something called type 1a supernovae, were moving away actually more quickly than expected. They were fainter than they anticipated, and this has been interpreted for the last nearly 30 years now, that rather than the universe's expansion slowing down, which is what everyone expected due to the effects of gravity, it seems to be speeding up. And it is this is attributed to something called dark energy. We don't know what dark energy is, but the observational evidence seems to point, based on type 1a supernovae, that the expansion of the universe is actually speeding up rather than slowing down. So we then need to modify the diagram for the possible futures of the universe. And so this is the more modern version, and that is that there is, some people still think that the universe could actually stop expanding and recollapse in what people sometimes refer to as the big crunch. But it's more likely that because of this dark energy, because of the acceleration of the expansion of the universe, that the universe will not only carry on expanding forever, but actually the expansion may well speed up. So we have what we call the big freeze, where things expand forever and all the stars die because they use up all their fuel, or the big rip, which is when the expansion of the universe accelerates because of the dark energy and accelerates more and more quickly. So the current favorite model, or the model believed by most people at the moment, based on the evidence that we have, is that the ultimate fate of the universe is the big rip. And I will finish my talk there. Thank you.
Thank you, Dr. Evans. Raza, would you like to add something to that?
No, thank you for answering my question. I don't have anything more to add. Great.
I think I'll just keep moving. If there's time left at the end, perhaps we'll go back a bit. Anyway, thank you, Dr. Evans, and thank you, Raza, for that. Now, our second question is from Maropula Science and Astronomy Club, and it's put by Mano Moran. He's in the upper sixth form at Maropula, and he's president of the club. Over to you, Mano.
Yes, hello. Can you hear me?
Yeah.
Okay, thank you. So my question is, how do we actually see a black hole if no light escapes from it? And how are these images of black holes captured?
Thank you. Professor Bode will answer that. Over to you, Prof.
Okay, I'm just fiddling about here trying to get my screen to share, to be honest.
This thing.
Right. I'm hitting share at the top right. It then goes into presenter mode. And maybe I should hit window. Oh, here we go. Can you see that?
Yeah, we can.
Okay, let's go from there. Okay, so this was question is in two parts really. How do you actually see a black hole if no light escapes from it? Well, no light escapes from a black hole, and we'll hear more about black holes in detail later on from Stuart. But really, we don't see them directly. We see their effects, mainly their gravitational effects on other things. And I'm going to talk about two well-known black holes. The first one is in a source called Cygnus X1, and this is an X-ray source in the constellation of Cygnus. You can see the constellation here on the right, on the left-hand side of the screen, and Cygnus X1 is marked. It's also noted as V404 Cygni, which means it's a variable star. And we now know that it's in this sort of system. It's two stars orbiting each other, or two objects orbiting each other. One is a star of about 40 times the mass of the sun, so a very luminous star. It's in a 5.6-day orbit with something else. And from the orbit and various other bits of evidence, we know it's orbiting something that has a mass of about 20 times the mass of our sun, but we can't see it. But we do see X-rays coming off. And what's happening here is the stars are so close together, or the star and the black hole are so close together, that material is effectively falling from the outer atmosphere of the star via what's called an accretion disk onto the black hole, where matter will disappear into the black hole at the inner part of the accretion disk. And as it falls down here, you've got gravitational potential energy being converted to kinetic energy, for example. The gas heats up and the X-rays are coming from right in the middle of that accretion disk. And they are variable X-rays. We can, even from the variability, we can work out the spin of the black hole, for example. So that's a 20 solar mass black hole. We now move on to much more massive black holes, supermassive black holes, which are found in the centers of galaxies. There's emission from around them where stars and interstellar material are falling into the black hole in much the same way as is being accreted by this stellar mass black hole, SIGX1, but on a larger scale. So we see that sort of emission from the centers of galaxies. But in our own Milky Way galaxy, we are, and the image on the left-hand side here is the Milky Way, an all-sky camera image of the Milky Way. So this is how you'd see the Milky Way if you were able to take a photograph of the whole sky. So this is putting together photographs of the whole sky. The center of the galaxy in Sagittarius is around here, and from Botswana you have a fabulous view of that area, which we don't have from the Northern Hemisphere, which, or at least this far north, where I am in near Liverpool at the moment. And in the center of our galaxy, we know there is a supermassive black hole because we've followed the trajectory of stars. So this is looking way, way down into the center of the galaxy. This is work that earned a team 4 or 5 years ago the Nobel Prize. We see stars in the center of our galaxy orbiting something. And from the orbits, you can use fairly simple mechanics, basically Kepler's laws. You can work out the mass of whatever they're going around. It turns out that it has a mass of over 4 million times the mass of the sun, but we can't see it. It's not emitting any light. It's a black hole. And in this case, it's a supermassive black hole. So that's how we can detect black holes without actually seeing them. And the second part of the question was, how do we image black holes? Well, again, we can just image the effects effectively. I should mention the Event Horizon Telescope, which is a configuration of millimeter wave telescopes at various locations around the world, acting as one telescope, as if it had the diameter of the Earth. So at millimeter waves with an instrument that's about the diameter of the Earth, and Rodri's been involved in this in the past, involved in a project to put a millimeter wave telescope in Namibia as part of this. You can get tremendous resolution, very fine detail resolution, such that you could see a donut on the moon or a CD on the moon with this sort of resolution. And this Event Horizon Telescope has been used to look at supermassive black holes, one in M87 and other galaxies, but M87 was the first one where they got some sort of meaningful image. This is the image that comes from the surroundings of the black hole in the center of our galaxy, so-called Sagittarius A star, so the very center of our galaxy. Now, Stuart is later on going to show a similar image, and we'll say a lot more about black holes themselves. But that is the best image, as it were, of the surroundings, the nearby surroundings of a black hole that we have. In this case, you're looking at something that's about the orbit of Mercury, the diameter or the radius rather of the orbit of Mercury around the sun across. So it's a very, very small, it's very, very high resolution, because you're looking at something that's a distance of nearly 30,000 light years away from us. So that was, that's what I wanted to say. I've got another slide, an animation, if there's a question on it, but I can leave that till later.
Thank you, Prof. Berg. Mano, would you like to make a comment or ask a question on that?
No, nothing from me. Thank you so much for answering the question.
Okay,
Great.
Thank you for the question.
There are 2 more minutes until this one. Anybody else, any other student, anybody else like to comment on what Prof. Berg said or ask a question? If so, now's the chance.
I can show this animation. If,
all right, show the animation.
Okay, this is a NASA animation, and this animation shows, you see this the dark area in the middle here, that's the so-called shadow of the black hole against the accretion disk, but actually it's a much more complicated picture, because you get bending of light around black holes, and this is an animation showing what you are seeing. So this is put together by a group of scientists who are actually working on this sort of thing, and you can see the distortion of the rays of light by the black hole, the way it distorts the accretion disk behind it and the stars behind in the background as well. So that gives you an idea of how this image up here is formed, and from that image they've managed to derive an awful lot of information on the supermassive black hole in the center of our galaxy and the one in M87 as well. But I know Stuart will say more about this later.
Thanks, Prof. That's lovely. That's a lovely animation. Okay. Yeah. Yeah. I was going to say, our third question is from Legae Academy again. And this time it's put by Dylan D'Souza, who's in the A2 class and who's been in that club at the school for a year. Dylan, over to you.
Thank you. Good afternoon, everyone. My question was, do you think there's life in the rest of the universe, and how do you think the research will progress in 20 years?
Thank you, Dylan. Prof. Fulvio Franchi is going to answer that. Prof. Franchi, over to you.
Yes, thank you very much for this question. So there is a short way to answer this question and a long way. So in short, one might say that, and I stand to be corrected by my colleagues here, that no numbers better than me, but there are around 100 billion stars in the Milky Way alone, and probably other hundreds of billions of galaxies in the universe. So the common answer to this question is that statistically, it is highly probable that there is another planet that is as lucky as our own planet Earth. Clearly, that is just a shortcut, is a yes, but we can dig more into this topic. And we can do that by answering those 2 points that I put on my slide. So what is the definition of life? And what kind of signs are we expecting as scientists when we look for life outside our planet? To answer the first question, I had to ask help from NASA. So, because the definition of life is extremely complex, it keeps changing with the progress of science. There is a new scientific discipline called astrobiology, which is not that new, but it really took off in the past 20 years. And it looks at how life originated in the universe. And this definition of life, it changed with the context. It can be a different definition for an astronomer, for an astrobiologist, for a biologist, and so on. So NASA provides the definition that we use in planetary science and says that life is a self-sustaining chemical system capable of Darwinian evolution. And the bottom line is that all living things that we are expected to be on our planet and out there have some common traits. So cellular organizations, the ability to reproduce, it grows and it develops, it uses energy and adapts to environment in different ways. So this is what we look for when we ask about life in the universe. Can you go to the next slide, Mike? Now, as a scientist that works in astrobiology, the other question is that how do we look, or what we look when we talk about signs of life? We're clearly not expecting any Kryptonian superhero or something like that, at least not when we work in my field. So initially, we can talk about biosignatures. So biosignatures are, again, evidences that can be analytically detected in a certain matrix that can be a rock, a sediments, or water that point directly to biological processes, and that cannot be explained in any other simple way that is not life as we define it. So the research for life in the universe started in the 60s and 70s, and it was initially very disappointing. For instance, the Mars Viking lander in the 70s found absolutely nothing on the red planet. But the planetary science progressed quite fast in the past decades. For instance, now we know hundreds of exoplanets, and some of which might be in the habitable zone of their stars. So in that region, that allows the presence of liquid water. We also found indirect evidence of past water on Mars, and you see it in the background of the slide. And also buried oceans under the icy shells of moons of Saturn, for instance. So the more we push the boundary of planetary exploration, the more we make discoveries even on our own planet, for instance. Ever since we started looking for extraterrestrial life, we realized that life on our planet, it's more resistant, is more widespread, and it's more extreme than we thought. So the research for life outside our planet actually made us understand better how life exists and came to existence on our own planet, expanding the limits of life as we know it. Anyway, Mars is probably still our main chance to find evidence of life. I put here in the bottom left a very small picture from the rover Perseverance that recently discovered mineralogical evidences for the presence of biological activity, past biological activity on Mars. So these are not fossils, but they are minerals that are linked with organic compounds that are considered biosignatures. So once again, they could be formed in many ways, but the simplest explanation is that there were bacteria on Mars within the sediments before they became rock that made some changes that induced the formation of this mineral. So and this was just the most recent discovery made by the rovers on Mars. coming to the second part of the question, so what do we expect in the next 20 years? Well, I'm a European who have been 10 years in Botswana, so I want to give you this information from the European perspective. The European Space Agency has just approved an L4 mission, so a very large planetary mission on the tiny moons of Saturn, which is called Enceladus. And the preparation of these missions are ongoing. Many of you will be my age by the time this mission is launched. Hopefully, I will not be retired because although Enceladus is a very tiny moon, just 500 kilometers apart, they are preparing a very exciting mission. They're also talking about drilling the ice, going underwater. So it's very exciting time. They actually start to build the scientific case and the payload that will go on that mission. So the answer to me in 20 years, astrobiology will focus on icy moons of Saturn and Jupiter. So it's not just Enceladus, but even Europa, Titan, and many other icy moons of the two gas giants in our solar system. I'm not touching too much on exoplanets because that is not my field of expertise. But as I mentioned, the discovery of exoplanets boosted a lot the astrobiological research because it basically proved what I mentioned at the beginning, so that statistically there should be a planet like our own or very similar to our own. So this, I think, answer partially to that question. David, over to you.
Yeah, thank you, Prof. Frankie. That's very kind. Very good. Dylan, would you like to ask anything or make a comment on what Prof. Frankie has said?
No, not at all. Thank you, Professor Frankie.
Great, thank you. Is there anybody else who'd like to say something or make a comment?
I'd like
Welcome.
to ask. I'd like to
Who's
ask.
Yeah, go on.
How a while back they dropped some research on Venus, and there was some chemical in the atmosphere which is produced by microbial life, but I haven't seen anything recently on like adding on to that. Has there been any progress about that on Venus?
Prof. Frankie, do you know an answer to that?
I don't know specifically what the student is referring to on Venus. I don't have much experience on Venus. What compound?
Maybe I should phrase my question better. A while back, they discovered a gas in the atmosphere, phosphine, which is on Earth is produced by microbial life in swamps. So they found phosphine in the atmosphere of Venus, which suggested there might be microbial life on the atmosphere of Venus. But after I saw that, I didn't see anything adding on to that. So I was just wondering, was any progress regarding that?
Not that I know.
All right,
sorry.
thank you. Thank you.
Okay, Prof. Bird, you don't want to add anything onto that, or anybody from the panel?
Yeah, I think this was from the University of Cardiff, researchers there, and it was a marginal result, possibly in conjunction with University College London, and they were due to follow it up, but I've heard no more. So maybe the follow-up, very often these things go away when you get more data, but like you, I heard about it at the time, but I've not heard any more since. So my suspicion is that when they got more data, they probably got what was called a 2 or 3 sigma result, and you get more data, and sometimes those things go away again rather than getting to be a stronger signal.
Okay, thanks, Prof. Bird. And thank you, Mano, for that question. Our fourth question comes from the Maropula Science and Astronomy Club, and it's put by Emmanuel Macheto, who's a Form 2 student and who's been in the club for a year. Over to you, Emmanuel.
Good afternoon. Can you hear me?
Yeah.
Okay. My name is Emmanuel, and my question is, beyond theory, is there actually a possibility of white holes existing?
Thank you, Emmanuel. Dr. Molokani Tsipa is going to answer that. Dr. Tsipa, over to you.
Oh, thank you, Chair. I don't have much to say, Emmanuel. I was also not aware that you are from two, or I was not aware. But I don't have much to say really, because myself, I'm not an astronomer, I'm not an astrophysicist, I'm just a theoretician. And the question that you are asking me is something that is outside theory, because you are saying beyond theory. So you are going beyond my area of specialty. But you know, white holes are a bit strange. Of course, even black holes, because you know, when we look at black holes, we can then see stuff falling in, and then maybe the black hole becoming heavier and heavier. But you know, when the stuff goes into the black hole, we are not really sure of where the stuff is going. All we know is that it's there, because we feel the gravitational effects of something massive being there. But we don't know where it is going, where it is. And probably that is why some people would then speculate that perhaps this stuff that goes into a black hole goes into to be matter in another universe, and it will be coming out from that universe as a white hole. So we don't know where this matter that is going into the black hole goes, because as you may or may not be aware, you know, the space inside the black hole is very, very large. It is larger than the space that can be measured when we are outside the black hole. So inside the black hole, there's a lot of space bigger than the space that can be seen from outside. So that is why maybe some people say when matter goes into the black hole, it goes to become a white hole, and it spews out into another universe, which maybe is connected by the wormhole of that black hole. So we don't really know, because also these white holes are, because if you look at a black hole in the usual time that we have, you can see stuff going in, but then if you reverse the time, then you see stuff going out, which is like a white hole. So a white hole is like a time reversal equivalent of a black hole, which still poses the question: if stuff is coming out of the white hole, where is it coming from? That seems to be a bit of a problem. And you know, when these things go out of this black hole, this is ordered matter, which is being ejected into our universe. Now, one of the physical laws of nature is that things tend to become more and more disordered in life. Like if you have a block of something that smells nice, you open it and put it there. At first, the particles are in an orderly fashion. They are forming that block or cube or rectangular thing. But later, you catch a smell because those molecules are dispersing throughout the space. So that is a natural law that we tend to observe on the overall when we look at the natural phenomena, that things become a bit disordered. Now, black holes, they increase this orderliness, whereas white holes, because if now they inject ordered material, then they will increase the order, which is against what we observe. And that this thing that we observe, where it's like things become more and more disordered with time. There are things that give us a feeling of the arrow of time. Otherwise, things when we look at events that happen in life, then we could be seeing things going back and forth. Maybe an egg being unscrambled and stuff like that. Coffee coming out of a cream and shattered glasses getting unshattered and stuff like that. But because of that natural tendency, we can then have this property of the arrow of time being imbued on nature. So some people have looked at the black holes because as you may know, black holes or rather energy or mass as the theory of general relativity of Einstein is something that deforms space-time so that gravity can, for example, be viewed as something rolling down the fabric of space-time that has been warped a little bit. So this warping of space-time, when the black hole is big, we can say it occupies a larger area, even though that might be leading to say a larger area. But we can just visualize to say if the black hole is larger than the curvature occurs on a larger area. But if, for example, people like Stephen Hawking theorized that perhaps black holes can radiate some bit of electromagnetic energy or some particles which may end up decreasing the mass of the black hole. So when that happens, then the black hole, since it is a black hole, it is still heavy. Therefore, the curvature in space-time is still quite considerable. But as it continues to get lighter, that region becomes smaller and smaller, where the curvature occurs. It becomes smaller and smaller, and then it will then go into very small regions of space. And when we go to small regions of space, we usually then invoke the laws of quantum mechanics. And since the laws of quantum mechanics work with probability, then as the black hole gets lighter and smaller and lighter and smaller, then the probability of it existing as a white hole increases, and then we can then have a black hole then transforming into a white hole because of that quantum bounce or a quantum jump. But it would take a very long time for the black holes that we have right now to evaporate, where they start to form white holes, if at all white holes can be formed in such a manner. And the other issue may also be that you know this because
Dr. Sipper, your time is nearly up.
Oh, yes. Yeah, I was hearing a bit of a noise, but let me just summarize. I wanted to say, a black hole, a white hole, being something that ejects matter. It looks like it almost looks like our universe that originated from a singularity, and it is expanding. It may look like that, but a white hole is something that is supposed to occur in a space time. So we cannot really make too much of an association between a white hole and our universe, or the singularity from the Big Bang. Thank you very much. This is all I had.
Thank you, Dr. Sipper. Emmanuel, we've gone a bit over time, so I think I'm just going to push ahead. Time at the end, we'll come back. Our fifth question comes from Legae Academy Astronomy Club, and it's put by Makonakaisha Muzunzini, who's in the A2 form and has been in her club for 2 years. Makonakaisha, over to you.
Good afternoon.
Good afternoon.
My question is a black hole capable of causing a rift in the universe?
I can't hear very well. Can you repeat that? There's some background noise. Say it again.
My question is, can a black hole cause a rift in the universe?
Okay. And to answer that, I'm going to ask Dr. Stuart Marongwe. Dr. Marongwe, over to you.
Thank you very much, Chair. That's a fascinating question, Maka. It's one that sits at the heart of most of the fundamental questions in physics. First of all, the previous speakers have talked about black holes. Now I'm going to explain a bit about their nature. We understand black holes through models or theories of gravity. One of the most important ones that we have is Einstein's general theory of relativity. If you look at the left of the screen, you will find a cartoon on how we try to explain the environment around a black hole. So you will see this rectangle. This is the flat space where no gravity is available. So we are depicting it in 2 dimensions. Yet we know that space is 3-dimensional, because Einstein's theory of general relativity explains space in 4 dimensions. So as humans, we don't have the imagination to think in 4 dimensions. So this is a better way to represent it. below the triangle, you'll find that that's the dimension of time, okay? So this is the structure according to Einstein's theory. It's a model that helps us try to understand the nature of these black holes. So what is a black hole? A black hole is an astronomical object with a gravitational pull so strong that not even light can escape from it. That's very powerful. That's why it gets its name from the American physicist John Archibald Wheeler, who says that this is a black hole because no light can escape from it. So once you reach this zone, it's called the event horizon. That is the place where light can no longer escape. Beyond the event horizon, we begin to speculate because we cannot see. As you can see, this is the best image, like Professor Bod was talking about. This is the best image we have of a black hole. You can see that there's a central depression, that's the black hole. And surrounding it, there's a glow of light, okay? It's an accretion disk or some surrounding matter. So what happens inside that dark zone is still a black box. It's a mystery. And when we use Einstein's theory, we discover that there is a singularity within the black hole. But what is a singularity? Now, if you see this green zone, once we escape, we enter the event horizon, time and space begin to switch roles. Space becomes time and time becomes space. So singularity is a point in time, not in space. And in physics, when an equation shows singularities, which means it can no longer explain the physics of what is happening. So people have been looking for better ideas to explain what lies within a black hole beyond the classical theory of general relativity. This is when the laws of quantum gravity begin to come in, to kick in, as Dr. Tsipa alluded to. We begin to, so we are working on quantum gravity to explain the nature of what takes place around and inside a black hole. There are various theories, but we still need rigorous tests to understand that. But so far, black holes do not rip the fabric of space-time, because if they did, it would mean a gap in space. And as we know, inside a black hole is time and space reverse roles. So to say, to answer your question in brief, black holes do not rip the fabric of space-time, because the beginning of the universe, just like Dr. Tsipa was saying, it started with the Big Bang, which created space-time and did not rip space-time. So we can really understand this question from quantum gravity perspectives. And we are hoping young people with such questions can study quantum gravity and help us understand what really takes place inside a black hole. I thank you very much for that fascinating question, Maka.
Thank you very much, Dr. Marongwe, and thank you, Maka, for that question. I'm just going to push on with time. We're getting near the end. So our sixth and last question is from the Maropula Science and Astronomy Club, and is put by Zamam Anwar. He's a Form 4 student who's been in that club for 2 years. Zamam, over to you. Zamam, are you there? If not,
I think Zamam's been feeling unwell, so she's not present today. So is it fine if I ask on her behalf?
Yes, that's a good idea. Go for it.
Okay. So this question was put together by everyone in the club, and we wanted to ask is if Botswana was capable of launching a space research satellite, or if it has been done already, and if any other African nation has achieved success in doing so.
Thank you. And Prof. Bode will lead the panel to answer that. There's no one, but I'll give it over to Prof. Bode and he'll organize the answering. Prof, over to you.
Okay. Thank you, Mr. Slater. Yeah, I thought we'd answer this as a panel because there are different amounts of expertise and views on this across the panel. Botswana itself, of course, has seen a satellite launched in the last, well, I think it was launched in March. This is a CubeSat. It was actually launched on a SpaceX rocket from California, along with several other satellites. It was a co-launch with those. Other people here may know more about what BotSat is doing, but I think it's mainly an Earth resources, and it's not an astronomical satellite as such. It's looking the other way down at the Earth. And so Botswana has a satellite in space. It didn't launch it itself. I'm not sure other members of the panel will know whether any other African country is capable of launching a satellite at the moment. But certainly other countries in Africa have previously launched or had launched space satellites. I wonder whether, Fulvio, you have an overarching view of what's going on in Africa, because you lead a Pan-African project in planetary science. I just wonder whether you might say a few words about this, and then we can open it up to the rest of the panel.
Yeah, you mean overview of Africa?
Yeah, because what part of the question is, do other African countries have the capability to launch satellites? And I was saying that other African countries, South Africa, for example, has had a lot of satellites in space.
Yeah.
But I don't know that they have the capability to launch them themselves.
Yeah.
Yeah. Okay.
Well, the problem that even Western countries are facing is the launching part. So missiles, like rockets. So no African country can do that. But don't worry, even Italy or many European countries cannot do that by themselves. Okay, so that's not actually a big deal at the moment. It will be in the future, but right now they are mostly commercial rockets like SpaceX and Blue Horizon in the future that will launch satellites. In terms of technical capabilities, many African countries are very well positioned in space technology. There is okay. Let's leave South Africa on a separate category, but there are clearly Nigeria and Egypt, many of the countries in the north of Africa. There is Ethiopia. Zimbabwe is working at a similar project like BotSat-1. There are several satellites from Kenya. Rwanda has a space agency that is aiming at a similar project to BotSat-1. So these are clearly all satellites that are looking down. So for remote sensing, because that's where the interest of many African governments is. Also, you should know that there is an African space agency, which is hosted in Cairo, the capital city of Egypt, and it's backed by European and African Union money. So in short, when we started, 10 years ago, very few countries were able to compete in the space economy. As we speak, as of today, basically, probably 80% of the African countries have a project for space technology, or they are already playing their role in space technology. When I say that, I mean they have at least one satellite, or they're about to launch a satellite. So there are companies in Cameroon that are assembling, they are teaching people how to build satellites made in Africa for Africans. We did the same with our project a few months back in Cape Town with colleagues from Zambia. Zambia is investing a lot in space technology. Well, let's say in remote sensing for now. So yeah, there is plenty of investment, let's say interest in Africa concerning especially remote sensing. Remote sensing is a bit the gateway to space, because that's where governments see the money coming in and the benefits, but that will open to other aspects of astronomy and space science.
Thank you, Fulvio. Do other members of the panel want to chip in at all? Rodri? Yeah.
Yes, I just wanted to, if I can share my screen, I can quickly show a website that shows a summary to date of the satellites launched by African countries. So let me, if I can get this to work. So hopefully you will now see in a web page, the URL is spacehubs.africa/regions, and it says that there are 67 satellites that have been launched by 18 African countries. As Fulvio says, they're not launched by the countries themselves. They are developed in those countries and then launched either by the European Space Agency or SpaceX. But it seems that Egypt and South Africa have launched the most satellites, and Botswana is included there because it's the latest one of the ones listed to have launched a satellite. So it seems this page is pretty up to date. And then if you scroll down, you can find out more about what's going on in each region, the 4 different regions there. So the students may want to look at that in their own time.
Thanks, Rodri. That's very informative. Yeah.
Anyone else?
Okay, I just wanted to add on for the student who might be interested in rocketry research. There's a test, the overberg test range in South Africa. They are testing suborbital rockets.
Oh.
Yeah, so if you want to learn more, just look for the overberg test range.
Thank you.
All right.
Okay, we've got 2 minutes left. Can I use those 2 minutes to ask Prof. Bode to give us a quick feedback? What do you think of this, our first Q&A session? Prof?
Oh, well, first of all, David, thanks for organising this. Thanks to everybody in the schools that's taken part and the panel members. I'm very impressed by the quality of the questions. We had probably twice as many questions as we were able to deal with today. So if people generally think this has been a successful thing to do, then we can repeat it and maybe pick up some of those questions and some more questions. I think the main feedback should really come from the students themselves and their teachers as to how useful they think this has been. But from my point of view, I think it's been a great thing to do, and I've really enjoyed it. And I've listened and learned some things myself from 1 or 2 of the speakers as well, which is always a good thing. So, yeah, thank you.
Thank you. And I'd just like to say thank you very much to you and to your panel, because I thought that the answers were so very well presented and so thoroughly looked into that it was very good. I loved it. Thank you very much. And I think I'll take up your point and I'll talk to the students and find out what they think about this. And then we'll see if it wants to be repeated. And I think that's the end of our session. We've done a full hour. We managed to get through all 6 questions, and that's very good. And so I don't know if there's anything else to say it now, and otherwise I'll close the session. Anything else? Okay, not. All right. Nope. Thank you. Thank you very much, everybody. That's the end.
Thank you.
Goodbye.
Bye.
Thank you.
Bye.
Thank you much.
Bye. Bye.
Thank you.
Bye.